Okay, so one of the first things you should do when somebody has a PowerPoint is look at the number of slides that they have. It doesn't actually show there, but there's about 60 slides. Oh, geez, we're going to be here all day. No, we won't, because some of them are just screen grabs and we'll whiz through them. So I'm going to talk about, so first of all, thank you very much for inviting me. Clean, it's a pleasure to be here. My first time in New Zealand. I've already promised myself it won't be my last. I was going to bring my Irish rugby jersey and hang it here, but there ain't no point anymore. No point. So I'm going to talk about life logging techniques for recording the self and how it interacts with personal big data. And I'm conscious that later on in the agenda and the program for the day, other people like Ralph and Cleena will also mention and include life logging. So without wishing to intrude on their space, I've retreated from your space, and I'm going to focus on the kind of analysis you can do on visual life logs, which means that you guys can have smartphones and other kind of things for your own space, so there'll be no duplication of what we do. Life logging is it's a term which is becoming popular, and it represents the phenomenon whereby people digitally record their daily lives in ordinary lives, not special people, just ordinary people like you and me, with varying levels of detail for various purposes. So it's about self-recording, and we've been doing this for, since the beginning of time, recording through diaries, things that we do. And now we can do it digitally, we can do it much more comprehensively. And with wearable technologies, we can do it automatically as well. And what a life log does is it creates a comprehensive or potentially comprehensive black box of a human life. So you can go back and you can refer to that black box and quiz it and mine it for useful information. And it arises because we have a convergence of technologies which foster the emergence of life logging. Storage has become significantly cheaper. It's now virtually zero cost to store huge amounts of information. But there's also advancements in sensing technologies, which means that we can have efficient sensing of personal activities, locations, and our environment. When you combine these two together, then the technology is in place to automatically record the things we do day by day by day. It also comes about because of the popularity of the quantified self movement, quantifying the self, measuring the self. We like to do this, and this is something that humankind is increasingly drawn towards, measuring ourselves, recording ourselves for various purposes. And we can do this using wearables and sensors to better understand our performance in a variety of tasks. So it's a form of first-person digital ethnography where the data sources which can feed into the life log can vary enormously. The most ubiquitous and the most useful source of information like this is the phone, the smartphone, because it has so many built-in sensors. And we'll hear some talk about that later in the day. But there's also wearable sensors, which are on-body sensors, which can record. And it presents wonderful challenges in the area of sensor technologies, because the body is a hostile environment for sensors, right, to wear sensors on a day-by-day basis. It presents challenging computer networking, device manufacture, data management, battery longevity, data alignment when you pull together all that data from different sources, analysis indexing, automatically summarizing or extracting useful information, searching or browsing through life logs, interfaces, the ethics and the privacy of a life log. So if I record something, it's mine. And what are the conditions under which I have to share that? The security, the data security, the ownership, and even the legal frameworks. So if I take a picture, if I'm wearing a camera and it's taking a picture of you, who owns that picture? It's your face that's in it, but it's my picture that took it. And what happens if you were doing something illegal, like parking on a double yellow line? Am I obliged to report that back to the authorities? So there's lots and lots of legal ownership and copyright nightmares associated with it. So who would use such a life log if it existed? Well, people who want a digital record of their lives would use life logs or would help to create life logs. And it's a very broad term because what they can do, especially if we use wearable cameras, which is what I'm going to focus on, other people will focus on smartphones and other wearable sensors. But the automatic visual diaries are a very rich source of mining information about day-to-day activities. People would also want to record their life visually because they want to share experiences with others. Now, share experiences like a weekend somewhere away or a skiing trip or something rather than the day-to-day things. That's normally what we do, but sharing everyday experiences could also be done with this. One of the first and most successful applications of visual life logging is helping people with memory difficulties, Alzheimer's and other dementias. They have short-term memory recall problems, but when you show somebody a picture of what they did yesterday, it then triggers a cascade of memories. It's called a Proustian cascade of memory triggers, and that's what happens. Okay, So studies we've been working with people with memory difficulties, acquired brain injury and Alzheimer's show that we do get short-term memory recall benefits when we get triggered by pictures taken from a first-person view. Medical and other professions and security professionals. So in the UK, police have wearable video cameras which they record on board, and earlier this year, Obama announced a US federal program with $250 million in wearable cameras for police forces throughout the US. Okay? And there could be many more applications of visual life logging, including rugby referees. But the rugby referees don't yet use them properly. Mr. Joubert, if he was able to recall, now think of that, okay? So he's there, he's looking at the big screen. If he was allowed to use that, if that camera, which we all see, right, was able, and if he was able to see, then we wouldn't have Australia in the semi-finals. Wouldn't that be good? Okay, so the sources of lifelog data that can feed into this, right, are many and varied. There's data which is captured about us by others, for use by others, but it's never directly available for us to use. And this is data we can't incorporate into our life logs. And this is the true application of big data. So every time you click something, every time you're online, every time you press a button, every time you swipe something, you post something, you like something, you view something, etc. From the obvious ones like Google giving you answers to queries, to the script that is used in House of Cards. You've seen House of Cards on Netflix? You know that wasn't written by people, that was written by algorithms. Because what Netflix did was they took the 33 million subscribers, they looked at all the times you pause movies and replay parts of them, and they analyzed what kinds of things people like in TV series across 33 million of us, and then from that they mined the most likely settings and scenarios and storylines that would lead to a blockbuster series, and that's how House of Cards came about. Okay, so every business from Google to Tesco, every application uses big data and mines it in a host of ways, and all of this is very unregulated, which is kind of frightening because Tesco and Netflix and Amazon and Google and eBay can do what they want with that data, because the regulation is very difficult to enforce. In Europe, right, because so many of these companies like Facebook, LinkedIn, PayPal, eBay and so on have their European bases in Ireland, it is the Irish regulatory authority which is responsible for defining and implementing the regulation associated with the use of big data, which is kind of frightening, Clean, isn't it, when you know what our Irish regulation system is like, especially with what we did with banking regulations a few years ago. We didn't have any. So that's the first source of information which we can't get access to feed into a life log. Second source of data is data which is about us, but which is captured by third parties, but it can be used by us. In other words, there's somebody else recording things about me, but I can get access to that data if I want to, and I can bring it in and I can use it in some ways. And this is sometimes useful, and it's sometimes it can be included into life logs. One of the best examples I have for this is in an iPhone. So if you've got an iPhone, right, and you want to take part in this game, and if you go to settings, right, I'm just going to have one person. If you go to settings, and then you scroll down a bit and you look for privacy, there's a tab called privacy. It's got the hand up icon. And the top of that has got a tab called location services. And if that is already switched on, then click that, okay? Location services on. If you scroll down to one right at the very bottom called system services, right? And then if you scroll down to the bottom of this, it's obviously one that's not meant to be found easily, is it, folks? One down at the bottom called frequent locations, and it will give you information on your frequent locations. Jesus. So read what it says about me there.
Oh.
Yeah.
Auckland.
Auckland? So this has been recording things about Auckland, me in Auckland. 5 locations, including Durham Street, Auckland, Wellesley Street, Ray Emery Drive. If I go to Durham Street, it gives me a map. Jesus. Right? Now this is an example of a third party recording information about me which I would like to be actually use and be able to get access to, but Apple don't do it that way, right? Another example of data which is created about us by third parties which we would like to include is in energy meters. Do you have smart energy meters in Australia? Yeah, okay. Do you have access to your own data? No, you don't really, right? So there's something in your garage that is pumping, right, and a signal which is generating smart energy meter, which is your usage on a regular basis. And there's attractions of data collection, because it means that the operators can just upload your data. They can have load-based tariffs. They can give you real-time feedback on your usage compared to what you should be using. And they can manage peak demands by imposing load-based tariffs to smooth out demands. But it's not easy to get your own data. So what we did as an experiment at DCU was we deployed our own homemade smart metering to 24 homes right across the country, right, with the same kind of fidelity and accuracy that you get with the smart meters that are used by utility companies. And we monitored electrical consumption within the home on a per minute basis. And we generated this kind of useful metric. So this is 0 o'clock in the morning, midnight, right up to 11 o'clock in the evening. And the top line is Monday, Tuesday, Wednesday, right down to Sunday. And the color codes indicate, the heat map indicates the peaks of demand. So you can see right across the country, you're getting the usual 5 o'clock to 7 p.m. Monday to Friday as people come home from work, with a little bit in the mornings and an awful lot greater spread throughout Saturday afternoons. And we generated nice ways in which we could feed this information back to people, so you could see your own usage versus your average usage. You could see whether you're above or below your usage, and that was really interesting. What we did though is that these usage of smart metering and energy in homes allows for tariff-based pricing, but it can be used for other things as well. Every electrical device that you have, which is a major consumer of electricity, like a washing machine or a dishwasher or a kettle or a water heater, but not a smartphone charger, for example, like a toaster, these kind of appliances, they each have a signature, which is the time that they're on and the load that they consume. And what we did was we used a machine learning algorithm to learn the signatures for different devices: toasters, kettles, microwaves, all of those heavy duty things, right? The ones that cause large peaks. Because how long does it take a kettle to boil? It takes whatever it takes. It doesn't take 10 minutes, right? And it doesn't take 10 seconds, right? It depends how much you fill it, of course, and how hot it is from the previous filling. But using the time duration and the peak of its energy usage, what we can do is we can train a machine learning classifier to recognize appliances. And we did this in the 24 homes, and we learnt the usage of different appliances in the home. Initially, it was done as an offline and archival process, and then we were able to do it in near real time. And it gives you useful information like this. This is the year, this is the annual year, the total year of, can't remember which year it is, of kettle usage in my house, Mondays through to Sundays. So you can see there's me up at 7 o'clock every morning, right? And the family's up and we're all gone. And there's nobody there. And then this is the usage of the evening. And this is Saturdays and Sundays, right? More use. So this is a form of third-party information of kettle use, but you could incorporate other devices, which could be useful and which could feed into a life log. And it represents the second class. Most of what we're going to talk about and of interest, which is about data captured about us, but captured by us, not by a third party, directly by us, for use by us. So this is applications of personal big data as opposed to corporate or enterprise big data. And because we don't have easy access to this kind of data, and we find it really impossible to get even this kind of data, most of the life logging work that goes on is data captured by us directly rather than ingested from a third party. And this is where the business end of life logging takes part. In visual life logging, this was really kicked off by a device called a SenseCam, which is this thing here. It's worn around the neck, and it has a front-facing camera, and it sits there. It is not meant to be hidden. It is not meant to be camouflage. You're supposed to look at it and go, oh, you're wearing a thing around your neck that seems to be taking pictures. So there's no idea of hiding it. It's a color camera with a VGA, so it's not quite the quality of a computer, the laptop screen that you have in front of you. It's got accelerometers, it's got a light intensity meter, it's got a passive infrared sensor, so it's able to detect when people walk in front of you, and it's got a digital compass, so it's able to get orientation. And it's got about 1 gigabyte of flash memory, which means that it can store on board all of this data, and its battery life is about a week. It has smart image capture, in that because it's got accelerometers, if you're doing this kind of thing, it's not going to take a picture because it's just going to be a blur. It's going to wait until you've stopped. It stopped. Take a picture. Okay, right? And it will take a picture on a regular basis at an appropriate moment, maybe 2 or 3 of these pictures a minute, which when you add it up is several thousand images on a day. Okay. Most of the images are very blurry, right, because there'll be a lot of movement, and most of them are very boring. But when you put them all together, you get a good visual life log or a visual diary of the person or the wearer. It represents one of a collection of life logging devices and wearable cameras, but it is the one which is most popular because you can wear it almost like a pendant, and they are decreasing in size and increasing in their battery life. The kind of images you get are these, and these mean absolutely nothing to you, right? But they mean an awful lot to the wearer, because the wearer knows who that person was. The wearer knows who that person was, and that person was, and this. And this is a typical thing, because if you're wearing a camera and you're eating a banana, you're going to get a picture of the banana, right? So there's a lot of hands that goes on, especially there would be with me, because I do this a lot, right? So a lot of hands goes on, a lot of food, a lot of steering wheels if you do a lot of driving, okay? That kind of thing. And these are the kind of images which are captured. Sometimes the images are nice, they're almost photogenic, right? This is Philo's statue in Dublin, Phil Lynott, right? And this is another artist fair that was going. So these are quite nice pictures, right? Sometimes, occasionally, you might get some nice looking pictures that you might even be proud of or put into an online photo album. But mostly they're not. This is a boring picture. This doesn't sell anything at all. It's the back of people, right? But when you put together the series of images associated with that walk or that walk, then it tells you a lot about the wearer and what he or she was doing at that time. There's some nice image processing challenges, right? Because it's a fisheye lens, because you don't want to have this as your picture, right? Because you're missing all the good stuff, right, all there. So you have a fisheye lens, which has got this warping of the sides like this. And you get pictures that are so close up of something like this, you don't know what they are, right? So this is an example of how the straight lines, our building really isn't like that. It does have straight lines in it, but this is just the fisheye lens effect. And you get movement. That's this constant movement. What kind of data can you gather with this? Well, one of our colleagues, Cathal Gurran, has been wearing the SenseCam for about 8 or 9 years now, every day, okay? Just because it's one of those things that you start doing, it's hard to give up, and now he's committed to it, and he's now made it his research work, okay? His own life log. So if you consider in a year that there's over 500,000 minutes, or 394,000 for an 18-hour day, he's identified in a given year about 12,500 events, where an event is like this. Me standing up here for 40 minutes is an event, okay? Me sitting down there for 5 minutes or 10 minutes before that is another event. Events sometimes are short and sometimes they're longer, but they're discrete and they're non-overlapping. And he will gather about 1.5 million SenseCam or wearable camera images in a year. He uses this in order to build up an archive of his life, which he can then have as the focus for his own research and for analysis, and I'll give you some examples of the things he's learned. He also has, from a wearable accelerometer, 115 million accelerometer, temperature and compass readings, 3.2 million GPS points, and what he also has running on his smartphone is an application that he calls the Bluetooth sniffer that just picks up the Bluetooth signatures from all of the other Bluetooth devices, including all of your smartphones, which are in range, okay? Most of the 25,000 he picks up are from him going through airports. So he's picking up total randomers. But occasionally he'll pick up somebody, and then he'll pick up that somebody again somewhere. And it might be just randomly meeting or being in the airport at the same time twice. But sometimes, if the pattern is frequent enough, then he can mine a friend or a contact or a colleague. Or maybe he just goes to the same church as, something like that, okay? So these are the kind of sources we have for inputting into life log data, in particular visual information. So what do we do with all of this information? Where do we start organizing it? Well, we're very forgetful, right, as a species, and we've been finding ways to substitute for our own memory for a long time. Our life experience memories are encoded into episodic memories. So this is an episode. I will remember this because it was an episode. And there will be triggers that will remind me of this episode, such as the fact that the screen keeps blinking out, or the fact that I have to give you back your MacBook connector, little things like this. Unknown events will then trigger recollection of this. And if we don't use our memories, then they'll start to merge and decay. This is a wonderful room. I've never been in this room before. I'm likely never to be in this room again, and therefore I can, faithfully, flush out from my memory the color of the carpet and the color of the walls. Unless I come back here next year for some reason, and they've done something different. They've painted the walls, or changed the furniture, or rearranged things. At that point, deep in my memory, I will recall my memory of what this room looks like. And that's the way our memory works. Unless it's used on a regular basis, it will start to merge and into decay. Those memories that we have and that we constantly create, they're linked together across multiple dimensions, such as sounds. Have you heard that sound? Hear that sound? Where did I hear that sound before? Or smells? Where did I smell that? Where did I smell that before? And we connect things from our past via these links based on sights versus smells, sounds, objects, feelings, emotions. I haven't felt so happy since the last time that kind of thing. So that's how we work. And when we recall memories, we create stories from these episodes. And we put these episodes together into stories. But even recalling these episodes is prone to error. If we have a digital life log, a black box of ourselves, a ground truth of all of our memories, then these electronic memories, or triggered by these visual pictures we've taken by ourselves, can encode all of life experience in a non-decaying archive. Oh, that's frightening. Because one of the great things about memories is that you forget things. But a digital memory doesn't let you forget things. So there's really lots of challenges with managing a life log and forgetting things from a life log and knowing what's important. So the way we've addressed the challenges for life logging are event segmentation. So take all the pictures you take during a day and divide them up into discrete non-overlapping events. Identify which events are novel or which are different to your normal day-to-day type things. Associate events with other events by linking them based on similarity, and then support some sort of browsing or navigation or story creation as a result. Event segmentation is actually quite straightforward. So here's 4,000 or 5,000 images which are taken from a wearable camera. Put them together like this, and what happens is that you identify changes just by colors and textures in those images. So if I'm wearing a camera, and all these pictures are going to be all of these colors, okay? All these colors. And then afterwards, when we go for coffee, it will be a different color. So all you need to do is identify major changes in colors. And what we do is we employ visual features and output from other sensors to take a day's life log and to divide it up into discrete, non-overlapping events like this. Okay? And then we can select one key frame as a summary for each event, and we can present a browsing interface to that. So event annotation, so this gives us event segmentation. But taking that event and then describing its contents is the next challenge. So using all sources of context for that life log, such as the location, because the SenseCam or other devices can get GPS, such as the Bluetooth devices which are in the neighborhood, such as the time, the date, etc., plus derived knowledge such as activities, and then integrating all those together, we can populate this with an automatic description of what that event is. So what do I know about this? Well, there's a sea of faces. There's at least 50 Bluetooth devices at this location, therefore it's likely to be a presentation. Why is it likely to be a presentation? Because all of the faces are looking at me. Whereas when I sit down, it'll be a different scenario. Same kind of event, right? But different things that will be pointing to different activities. Also, if I'm wearing one of these LifeLog sensors, I'm very active. I'm moving around, whereas for the rest of the day, I intend to be sitting down, okay? We can automatically analyze the images to determine specific concepts which appear in those images. So we can detect the presence or absence of a steering wheel automatically from the image. Wow, how do you do that? We'll see some examples of that. Or whether somebody is shopping. How do you make shopping? Think aisles of products and shopping trolleys, right? Visually distinct. Or the inside of a vehicle, in other words, not the steering wheel when you're not driving. Or a toilet or bathroom or giving a presentation. And these percentages here indicate the accuracy with which we can automatically determine the kind of event that is going on and the content of the images which constitute that event. So we've taken a life log, we've broken it up into maybe 20 or 30 different events, we've assigned some concepts to describe it, and they all sit there in our memory archive. What we would like to do is to recall the things which are novel and which are unique. Now, I don't know about you, but my breakfast every day is pretty much the same breakfast every day, right? I have the same combination of orange juice, muesli, cereal, tea, toast, bit of marmalade, etc. Sometimes I have it standing up if I'm rushing, because I'm doing other things and I'm trying to make lunch, sometimes not. Okay? So there's a boringness and a repetitiveness associated with me, and therefore it's not a novel event. When I go to give lectures, it's normally the same lectures in the same week to the same people, in the same crowd, and the same happy faces. Sometimes happy faces, right? So it's day-to-day things. So the things that stand out in my life are the things that are different, the novel things, the new places, the new faces, the new events, the new times, right? So detecting novelty is detecting the difference between an event with all of its images and other events, right? And that's easy to do because you have a set of images, right, which you're comparing against another set of images. And what makes an event different or unusual or novel is measured in terms of its date, its time, its location, the people encountered in it. And we can characterize every event by these things in order to determine novelty associated with lifelog events. Once we've identified the events and the novel events, we can then take an event and link it to find similar events, similar looking events, right? So I'm giving a presentation in front of this sea of 100 faces. And last week, or the week before last, I gave a presentation in Brussels, and it was a sea of faces, and none of you were there, I think, okay? But there's a similarity between the event, in that it was me being active for 40 minutes, standing up and walking around, driving the cameraman as I'm tracking from side to side, okay? And faces looking at me. So there's a way in which I can create a link between this event and the event last week in Brussels in order to create connections between these. And that's what we do with the automatic analysis and the integration of lifelog events. They're based on visual similarity. They're based on date and time. They're based on location and people. And they're even based on external factors such as the weather or the environment. And we've created a browser for a lifelog that looks like this. I'm not going to spend time on it, but basically it's got a calendar, click on a day. This is an entire day divided up into the 20-odd events. The size of the keyframe is proportional to its uniqueness compared to the rest of the day or the rest of the week or month or window in which it's around. You basically mouse over this and it will start to play back all of the keyframes from it. And then you can create a link, or you can do a search from, this is an event where I'm meeting Aidan. Find me other like events or similar events which are visually similar, and I can get a ranked list of other meetings with Aidan or with Gareth or with Naz or whoever it might be. So it's a way to browse through my visual life logging through a browsing interface. However, browsing interfaces are only good for small data sets, and they're only good for browsing through content that you know of and that you're familiar with. But it doesn't scale to very large volumes, and it only works well for your own life log. One of the things we'll hear later on is a project called KidsCam, where we're gathering, or where our colleagues in one of the projects here are gathering huge amounts of information on other people. And if I was to browse through other people's life logs, it wouldn't mean anything to me. So browsing is only good for something. In effect, what we need to do is to be able to search for memories, or search for objects, or search for events, or search for things in life logs. And that's where the real challenge is. So the way in which we do this, sometimes we want to do it for specific purposes, like we're doing in KidsCam, looking for dietary intake, looking for food intake. Sometimes it's for browsing for visualization. So this is think of this as being a large flat screen with multiple screens together, and all of these colors correspond to the dominant colors in a life log. Okay, so that's another application that we looked at, is the dominant colors that influence people. And this kind of browsing, as I said, it's okay if the collections are small and you know what kind of things you're searching for. In that example I had, where I had steering wheels and insides of bathrooms and lecture rooms and giving presentations and hands, if you know the kind of things you want to search for in advance, then you can use annotations in order to manually annotate those images or those life log events. So if you have an access to Mechanical Turk where you can get some crowdsourced annotations, and you have a pool of labor and a strict interpretation of what annotations are, then you can take somebody else's life log, you can interpret it for them, and you can assign descriptor tags, just as you would with a YouTube video, for example. And that's generally what happens with life logging, that we take somebody else's content, somebody looks at it, somebody interprets what it is, and then somebody assigns some manual annotations to it. But as I said, this doesn't scale and it isn't practical. So can we automate the annotation? Could we build software? How good is computer programming and artificial intelligence and visual interpretation and processing? Is there software or are there tools now, artificial intelligence techniques, which can understand images in order to describe their content? Now, this is interesting from a visual life log perspective, but it's also interesting from an ordinary person's perspective. So you've all taken digital photographs, you're all on Facebook, you're Instagramming, you've all looked at YouTube and things like that, and you want to go and search for information. How do you do that? Right? Well, there's no software which is generally available that's used by the major search engines that can take a YouTube video or take a Facebook photograph or take anything like that you have that's visual and can analyze its content and can provide you with a description of what's in there. Right? That's not on Google, but it will be very soon. So how can it work, right? Problem with annotating somebody else's pictures is that annotators disagree. What's that? If I was to ask you, you'd say a sofa, you'd say a couch, you'd say cushions, you'd say living room. You'd all be right, none of you be wrong, but there's no consistency across them, okay? Annotators will always disagree. Give me one word to describe that picture. First word that comes into your head. First word that comes into your head. Lakeside. Mountains. Yeah. See, you're all right. Sometimes you'll say lakeside and you actually meant side of lake or waterside. There's vocabulary mismatches as well. Okay? So we really have a problem when it comes to manually annotating. But when a computer does some things, it can do it consistently. So it should be easy for a computer to take a picture, analyze it by looking at the pixels and say, this is a car, right? This is a mountain, this is a whatever. If you take a simple object like a car is very standard. They all have 4 wheels except the 3-wheel version, right? It's a fairly recognizable shape. There's generally 2 windows and a bit at the front and a bit at the back. Sorry for people who drive cars that have this now, or smart cars. And it shouldn't pose huge problems for a computer. They're different colors as well. To tag a car automatically. Well, it is difficult for a computer to tag a car automatically because this is a car. This is what a car looks like. This is the shape of a car. Well, it's everything. It's all of those shapes, right, and all of those angles. And that's just one car, one model from one manufacturer in one color, okay? The generic description of a car is much more, it's much broader. So what we do in image processing is that we extract low-level features, really low level, that mean nothing to us as individuals, but en masse to a computer mean a lot of content. We extract color, we extract texture, and we extract shape, and we extract the spatial arrangement of those things. And we also start to use features called sift and surf to extract content from images in order to describe them in low-level features. And we combine these things together to give a description or to train a machine learning algorithm. What do I mean by color? Well, you take a picture like this. You extract the color histogram. There's lots of, this is what the distribution of these would look like. You group these into just a small number of perceptual colors. You get a bar chart. In other words, you get a count of the number of red, green, blue, orange, gray, etc. pixels, and that's what the colors look like. What's the texture look like? Texture is a measure of smoothness or coarseness or regularity. This carpet is a fairly rough texture. Okay, it's a repeating pattern of squares, but it's a rough texture. And if you were to put your hand on that, it would feel like a carpet. But if you were to put your hand on the texture, it would feel very knobbly and grainy. This wall is smoother in texture, right, than the floor. I'm not talking about the surface of it. I'm talking about the color that's there, right? The color there is a smoother texture than there is in the carpet. And the black is really smooth altogether, okay? Now, not the color, not the feel, just the texture. And there's software which can identify textures just as it can identify colors. And there's a scale of textures just as there are a scale of colors. Shape is another thing that can be extracted automatically, right? Shape of squares, shape of leaves, shape of, people, etc. Complex shapes like castle turrets, etc. All of these things can be extracted automatically. And the last are the ones which are really difficult for us to comprehend. And they are called sift or surf features. And these work at the pixel level. So you focus just on a small area like this. You look at a handful of pixels, and you look at major changes in a handful of pixels. And wherever there's a significant change in the image, like the corner of a building or the corner of intersection of windows, etc., you index by that. Now, each sift and surf feature doesn't mean very much on its own. But when you have thousands of them, like you would have across the Arc de Triomphe here, and you get a pattern of the occurrence of these, then a pattern of the occurrence of these is used to identify similar patterns of occurrence. It's like imagine those 5 points corresponding to 5 corners of a window, right? And these 5 points corresponding to the same objects, right? It can be independent of scale or rotation or inversion. And it's a way to identify a pattern of things which occurs and then reoccurs in another image. And you might think, well, every one-to-one match doesn't mean very much, but when you get thousands of these, then you can identify that that thing there is the same as that thing there. Even though it's bigger, it's further away, different colors, and it's slightly twisted, this is a way in which image processing can identify similarity between the same object occurring in 2 pictures. And this is what Google image search does. Okay, so one of the things I wanted to do is, whoops, wrong direction, this one here. What I've taken is that picture there, which is just that picture there, okay? And I'm going to use that picture as a query by putting it into Google. Whoa, did you know you can do that? No, you didn't know. And what it does is, so this isn't matching text against text. This is matching image against image, not knowing anything about the image file name. So it's looking at the colors and the textures and the shapes, and it's found this as the closest visually similar. Okay? And you can see there is similarity, the background, the white at the top, and so on and so on. Okay? So Google's now starting to do that and to support that for people doing image content-based search. Okay? And it's useful. And it's nice to be able to give a live demo of what it looks like. So here's another example. So you take a picture like this, you plop it into the query, and it comes up with these ones here. It's good for finding other pictures of things that you know exist, right? And it works very fast. But it's based on indexing it not in terms of words or anything else, but in terms of colors and shapes and textures and so on. But how good can a computer get at automatically annotating images without any context at all? About 3 years ago, there was a major change in image processing and in image analysis when there was a huge improvement made in the way we can automatically use colors, textures, shape, sift and surf features to identify visual concepts. And it was an article in the New York Times from about a year ago which gave some airtime and some oxygen to this. Okay? So here's an example of an image, and you'd look at it and you say, there's 3 guys and they're playing frisbee somewhere and it's in a park, etc. A human annotator would say, a group of men playing frisbee in the park. A computer is able to generate a group of young people playing a game of frisbee. Completely hands off, just based on pixels. No GPS location, nothing else, just based on pixels. Human says, a young hockey player playing in the ice rink. I don't know where the young part comes from. And then if you look, it does look like a young boy or girl, doesn't it? You have to go very close to see that. But anyway, computer's best version of that is 2 hockey players are fighting over the puck. I guess puck is what they use in ice hockey. Okay, that's not bad. Human says, a green monster kite soaring in a sunny sky. Computer says, a man flying through the air while riding a snowboard. Yeah, it's not always perfect. Doesn't have to be, okay? Human says a person riding a dirt bike is covered in mud. Computer says a person riding a motorcycle on a dirt road. These are pretty close. Human says 3 different types of pizza on top of a stove. Computer says a pizza sitting on top of a pan on top of a stove. Not bad. Okay. Human says elephants of mixed ages standing in a muddy landscape. Computer says a herd of elephants walking across a dry grass field. Why did it get that wrong? Why do we think that this is a muddy landscape? Right? I guess it's because we see there's water there. We guess that's water, and this looks to be a different color to the dry part. So it's the muddy part that the elephants are walking in. I'm just doing my own knowledge base here, processing. And that's why I'm getting elephants of mixed ages, small, big, okay, standing in a muddy landscape. Whereas the computer said it's a herd of elephants, that's close to mixed ages, walking across dry grass field. Why did it think it was dry grass field? Because this looks like patches of grass, perhaps, as opposed to reflections of off-surface water. So, but it's still close enough, okay? So how is this done? Well, we're at the stage now where from a given image, we're able to identify things like a bouquet of red flowers, or a bottle of water, or a glass of water with ice, or a cup of coffee, or a plate of fruit, or a knife, or a fork, or banana slices, or etc., etc. And when we get all of those things together, right, we can infer that this corresponds to a meal on a table. So the way this works is that we identify individual things appearing, newspaper or iPad or whatever it might be, and then we combine all of those different pieces of information to come up with an automatic caption of what that description is. Here's other examples. So here's an elephant. Here's a person rides elephant past shop, right, are the tags associated with that. And then from that you can caption it as an elephant walking down a street. Or it's not red, it's not white, it's not blue, it's SUV patrolling beach shoreline on cloudy day while seagulls. They're the things. And then you can come up with your own caption for that. Or this one here, dog, fence, sheep, field. And then you can come up with your own caption of that. The ability to identify individual components or tags within an image can now be completely automated using machine learning techniques. You can do that completely automatically using machine learning techniques. Okay? And then from that you can put together your own captions, and I could give you some more examples like this. What happened 3 or 4 years ago was that a couple of guys working in a research lab, Krzyzewski et al., won a competition that image processing scientists have every year. Benchmarking or comparing ourselves to each other is something that's built into computer vision researchers. It's in our DNA. We've been doing it since the start. You may come up with a great idea, but it's only a great idea when you compare it with how that work performs against your colleagues and peers. So about 3 or 4 years ago, these guys won an annual challenge called ImageNet. They didn't just win it, they completely gazumped everybody. They completely set new boundaries in terms of performance. And they did this using an approach which is a form of neural network which has been around for about 20 years, but which people had abandoned and which they returned to with some clever twists and some clever techniques to it in order to do what's called a multi-layer analysis. And since then, from about 3 years ago, we're now all on that bandwagon, or rather we're now following that lead of great performance that was achieved by these guys in automatic analysis. And this kind of technique is now available, right, to each one of us. There's about 12 companies I know of, each of which have web presences, and they do all this through web interfaces, which provide services to do this automatic tagging for you. Just one chosen randomly. There's a company called Imagga, I-M-A-G-G-A, which is a Bulgarian SME working in Sofia, which has built classifiers like these for about 6,000 tags. So think of 6,000 things you might want to find in a picture. Well, mad woman, glass bottle, flower, pen, notebook, table, chair, There's about 6,000 of these things they know of. And if you give them an image, what they will do is they will take that image, they will run it against their 6,000 known things, and they will tell you which of those 6,000 known things appear in that image. So here's a picture of a deer in some scrubland and background. Shove that into Imagga's web page front end, and it will say 79% chance it's a deer, 38% there's bighorn, caribou, mountain sheep, bovid, I don't know what that is, animal, wild sheep, wilderness gold, mammal, etc. And I'm sure if you keep going, it'll get to grass, trees, etc., etc. Right? And it does this as a service. You can get 12,000 of these images done a month, right, for $14 US. 14? That's $14 US, right? And you can have up to 2 API calls per second. In other words, 2 images. You can't just take 5,000 of them and say, here, go, give them the answer back. You have to drip feed them, and this is the drip feed rate. And you pay more, you get a faster rate, okay? This is an example of a service which can do this automatically for you. But what happens if your tags, actually this is just, if your tags don't exist? In other words, what these do is they have 6,000 known things. But what happens if you want to search for something and you don't know whether it's one of those 6,000 things? Okay? This is a project we've just completed with the BBC called Axes. And what we're doing here is we're searching through about 4,000 hours of TV content, including the complete collection of EastEnders. If that means anything to you. Okay, there you go. Okay, right? So what we do in this is just a 2-minute video. I won't play the whole lot, I'll just play the first part. Up on the top, guitar. And we search through the metadata, the tags, and there's nothing there, okay? And then we search for guitar under broader terms, and we hit the go button, and chug, 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 and we come back with an answer. What just happened there? What just happened there was that we took the term guitar, and we looked for about 1,000 positive examples of a guitar and about 1,000 negative examples of a guitar. And we get our 1,000 positive examples from Google. So we took the query that was typed up there, sent it to Google image search, and got back about 1,000 positive examples of what a guitar looks like. How do you mean you got 1,000 examples? That means if you go to something like Google and you type in guitar, and you go to the image part, we use these. These are hundreds and hundreds and hundreds, ultimately up to about 1,000 positive examples of a guitar. And we loaded down these 1,000 examples, and we took another 1,000 examples of something that's not a guitar, and we trained a machine learning algorithm to identify the difference between a guitar and not a guitar. Once we had trained that machine learning algorithm, we then applied it to the 4,000 hours of video, and we gave the answer. And that's what appeared there. What? You mean in the time just between the search button and the little whirly thing going on that comes over the end? Yeah, in the time between they hit the search button for guitar, the little whirly thing comes on, and it comes back with the answer. Now remember, what we're doing is, this is a case where you do not have a predefined vocabulary of tags like Imagia would have with 6,000 of them. You're coming up with new things. Okay, right? We have another example, and we're going to type in car. Car. Go. Run to Google, get 1,000 positive examples of pictures of what a car looks like, download them all, build a classifier to make the difference between a car and not a car, and then, oh, it's already done the answer. Okay? Okay, that is real time. So it's obviously it's a playback video, but that is real time of what it looked like. Penguin. 1,000 penguins. This is what 1,000 penguins look like. Difference between penguin and not a penguin. Now, cars, guitars, and penguins are easy because they're very visually distinct. Penguins are like this, okay? They're white and black. Guitars have got that shape. Cars a bit more challenging. Tigers have got that texture. But it shows you the kind of things that you can do with this. So what's all this got to do with life logging? Going back to our problems with life logging, our problems with life logging are that we have manual annotation, and annotators will always disagree. So what we can do with those visual life logs is that if we are assured that the things we want to look for fall within the 6,000 topics that that company or choose your favorite company does, then you're happy. You can then go and ship off your life log images, thousands of them, to Imagia. They will do the analysis, and they will then give you back the answers in that vocabulary of 6,000. But if it doesn't fall within that vocabulary of 6,000, then you need to use something like I've just described. The pre-calculated, the pre-built 6,000 classifiers is available as a service, right? And there are a dozen of them at least. But this ability to create concepts on the fly is not yet available as a service. But that's where we're going. This is my last slide, cleanup, okay? Right, so what I haven't done today is spend time looking at life log applications in health or in M-Health. I know that's the topic of today, but it's going to be covered by others. I wanted you to get a sense of what was possible with visual life logs, not just today, but next year and a couple of years down the road. I haven't spent time looking at life log possibilities or applications because others will do that to complete the day. Life logging as a concept will grow. It's a generational thing. Young people will adapt to it much quicker than we will and are all much more open to self-recording. We already have an open market for services and products. We trade globally, and the swing to open will apply to this personal data. So I gather a life log. My smartphone gathers all of that stuff and my information. Shortly, I'll be able to get access to that information that's recorded about me by a third party, or that's recorded about me by me myself. And I'm going to have all this wonderful data, okay? And it's going to be wonderful because I'm going to be able to analyze my health and my wellness, but Jesus, I don't have the skills to do that. So what do you do when you don't have the skills to manage something, right? What will happen is that we will make our data, our personal data, available to third parties to have it processed and managed for us. There will be companies which will spring up, and I will say, here's my iPhone data. Here's my life log data. Go analyze it and come up with something because I don't have the time, the skills, the energy, or anything to do that, okay? Just like we do with our money. There are third-party services. They're called banks. They take our money, they mind it for us, right? And we trust them to do this. And what these third parties who manage our data will do is that they will cross-reference and merge and annotate and use big data in order to generate useful information from our data. There are examples of this in other areas, such as energy consumption in smart metering. So what you can do with your smart meter data in the US is you can make it available to a company called O-Power, who will provide you with insights into your usage compared to your peers. Being able to do this analysis in real time, in live and real time, will be critical, and we will do this because we are concerned with personal health reasons. Okay? Ooh, sorry, Rosie.